Now this is what we covered on Friday. All right, so I'm just going to quickly refresh again on it. The intermediate value theorem is very important when you get into calculus or next math class. All right, so those of you that weren't here on Friday, again, the notes will be up. I tried to put them up earlier today, but the internet was messing around a little bit. These notes will be up. And again, remember the intermediate value theorem says that if you have a graph and you have a function on that graph, and it looks something like this, say, we have point A and B, and let's say this is 2, and this is 9. All right. What the intermediate value theorem says is that this function has the y values. All right. The y values are going to be some place on this function where the y value is 3 or 2.1 or 8.79 or pi. All right. Because in order to get from a y value of 2 on a continuous function and end at a y value of 9, you have to go through, like you have to have a function value of every number in between 2 and 9. Right? That's what allowed us to say if we have this, so if I take this function and move everything down to like something like, say, this, all right, that's what allows me to say that if I'm looking at the point between A and B, that if it goes from being positive, or in this case, y values are negative, to y values are positive, I'm able to say, okay, there's definitely a 0 point, like right here between A and B. Because I know at least one place the y values go from being negative to positive. All right, and I know there's another 0 right here because the y values go from being positive to negative, and then there's a third 0 here where the y values go from being negative to positive. So I know somewhere in between there, all right, there's definitely a place where there is a 0. All right. Now, that being said, what we're going to look at today, just let me double check something real quick. We actually won't have too much. All right. So right now we're looking at what we call end behavior. All right. This will pop up frequently throughout the year, and it will also pop up from AP calculus. Okay. So end behavior describes how a function behaves, obviously, at either end of the graph. So when we're looking at end behavior, we're looking at what's happening all the way out to the right when x is approaching infinity, or all the way out to the left when x is approaching negative infinity. All right? So what we're looking at is, the question we're trying to ask is, what happens to the value of f of x? What happens to the y value as x increases or decreases without balance? And all that means is the same. As x approaches infinity, or as x approaches negative infinity, what's happening to the y values? Okay. So what I do have here is, so typically if I'm asking you what is the end behavior of the left, you're going to say the limit as x approaches the negative infinity of f of x. If I'm asking you on the right hand side, the limit as x approaches infinity of f of x. Because infinity is off to the right, negative infinity is off to the left. All right. So again, our goal here is, no matter what the function is, I want you guys to be able to tell me what is the end behavior. And there's some nice, easy little tricks that if you can remember some key characteristics of functions, then it's very easy to do. Okay? So again, this graph that we have here is just an example. All right. So if it's going down, or so over here, the limit as x approaches infinity of f of x equals negative infinity, because as x is getting bigger, so as x is approaching infinity, the y values are going down. They're getting closer to negative infinity. Y is, remember, y is equal to f of x. So it's basically saying the limit as x approaches positive infinity of the y values is equal to what? What are they approaching? Infinity. Over here, the limit as x approaches negative infinity of our y values equals positive infinity. Alright? Now, not always going to look at this. You could have somewhere where the left-hand side is x approaches negative infinity equals, or the limit's going to be infinity, and over here it's going to be infinity. You might have it be negative infinity and negative infinity. Okay? All depends on a couple of different characteristics of the function. Okay, so we got that? So, what we're going to do first is we're going to use the graph of f of x equals negative x to the fourth plus 8x cubed plus 3x squared plus 6x minus 80 to describe its end behavior. Support the conjecture numerically. Alright? So, the first thing that I want to do real quick is double check something here. Is I want you guys first of all to tell me, just based off of this function right now, I want you to tell me two things. I want you to tell me, one, what is the leading coefficient of this function? What? Negative 1. Alright? What is the degree of this function? How do we know that? Because, yeah, and also because the highest degree is 4. Alright? So here's what I'm going to tell you. The end behavior for a polynomial function is all dependent on what the leading coefficient of degree is. Alright? I'm going to need to double check some things. But first of all, we just look at this graph. Alright? And what I want you guys to get really good at is I want you to get really good at writing down what the end behavior is using limits. Okay? So if I pull up a graphing calculator and we have y is equal to negative, negative x to the fourth power plus 8x cubed plus 3x squared plus 6x minus 8. Okay, graph. Alrighty. I'm going to change this around. So, first of all, you guys graph is probably at mean 6, so I'm going to start there. Start with that. See what looks like. Okay, so that doesn't show me much of the graph. So, anytime that you graph something like this, and you really can't see much of the graph, you can't really see what the end of the line, it's not that obvious. What you want to do is you want to zoom 0. And hopefully this works. So you can see right there. Alright? And I'm going to zoom out. So I'm going to zoom out a little bit more. I'm going to go second window. I'm going to hit window. And I'm going to make my x max, let's just say 40 today. Alright, so there's my function. Now, so I just messed around with it because I want to see a little bit more of the graph. Alright? Now, as we look at this, you can see sort of the left end behavior and the right end behavior. Alright? The left end behavior, here's our graph. Alright? So, if we want to describe our left end behavior here, Our left-hand behavior refers to when the x values are going off to negative. Alright? So what we would say is we go, alright, the limit as x approaches negative infinity of f of x, or more sort of layman terms, what's happening to the y values as x approaches negative infinity. What is this function approaching? As the x value gets smaller, what is the y value approaching? Negative infinity. Okay? And then we look at the limit as x approaches positive infinity of f of x. Alright? Well, if we look at the x values as they're getting bigger, what's happening to the y values? We're going towards negative infinity as well. Okay? Cool. Yes, question. You are going to, you're going to want to know how to find the end behavior. Looking at the graph, it's easy to do that. But at some point, you want to do a problem with the graph, which is not, it's really, there's a table that we make, and it's very short. It's not that. Again, it's all based, the end behavior of each function is all based on the degree and the leading coefficient. So as long as you're able to identify the degree and the leading coefficient, guess what? You're good. Okay? So, that being said, now it says support the conjecture numerically. Now what does that mean? Well, that means that we want to be able to just sort of take a number and plug it into this equation and figure out figure out exactly what that it looks like. So what we do here, again, is the easiest way to do this is just you have your calculator, all right? So if we choose it, so we're saying as x approaches negative infinity, as x gets really small, the y value approaches negative infinity. Okay? So someone gives me a very small y value that's really negative. Who? Negative 800. Yeah, that sounds cool to me. So let's see. F of negative 800. Okay? Now, I don't feel like typing this off my calculator, so what I can do is I can use my calculator, and I can say, I can be like, okay, second window, we're going to a table, and you said negative 800, so I'm just going to type in, I want to start at negative 800. Okay, cool. The table step should be 1. Then hit second graph, negative 800, and it's negative 4 e to the 11. That means it's negative 4 with 11 zeros on the end of it, so that's a big, really negative number. It's this negative right here. It is negative 4, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Hundreds, thousands, there's negative 400 billion. I don't think that's ever coming back away from that. I think that's going to go to negative. You got negative 400 billion. Then, so you prove this. All right, so f of negative 800 is, and then what easy way to write that down, write all the zeros, is negative 4 times 10 to the 11. All right, and then I need to check it. We'll do f of 800 just because I'm going to do negative 800. Why not check 800? So we're going to go second window. We're going to check at 800 instead of negative 800. Second graph. Although, it's like the same thing. Negative 400 billion, or 400 billion, whatever I said. Clearly, it's going to negative infinity. And so again, it is equal to negative 4 times 10 to the 11. Okay? So, obviously, it's going, our limit, our end behavior that we just described is correct. Alright. Now, that makes sense. All we did is look at the graphs and the tables. Okay? Let's really look at another problem. graphs that approach a specific value. Okay. All right, so graphing it is a very good way to check your answer. All right, but you're going to want to get to the point where you don't have to graph every function. Okay, so what I'm going to show you, and I'm going to put a table up here that is a nice, easy guide to figure out the end behavior for polynomial functions. Okay, so we're going to add this here. When we're going to say end behavior for polynomial functions. Alright. So polynomial for end behavior functions, or end behavior for polynomial functions. Alright, so alright, so I'll make a quick table for this. Alright, there's an easy way out. Again, I said it all is based on your leading coefficient and degree. Alright, so what I want you guys to be able to do is I want you to be able to figure out the end behavior of a polynomial function and eventually other functions without having to look at the graph. Okay? I don't want you to have to look at the graph all the time. Because to be honest, there's going to be times that you need to look faster. You need to be able to just look at a graph and identify it. So, to make your life easier, and not have to type in the function every time you look at this, you're going to want to sort of take this into consideration, and I would memorize this. Okay? So, you have a couple options. And again, it's all based on the degree and leading coefficient. You're either going to, you can have a degree and leading coefficient. Alright? If your degree is even, and your leading coefficient is positive, okay? Your graph will look something like this. When I say something like this, I'm referring to the leading code. I'm referring to the end behavior. Your end behavior will take on this type of end behavior. All right, meaning that the limit as x approaches negative infinity of f of x is equal to positive infinity, and the limit as x approaches positive infinity of f of x is equal to infinity. Okay? If your polynomial function that you're working with has an even degree, so if the highest degree is 4, 6, 2, 8, 10, whatever, and the leading coefficient is positive, your end behavior will be positive infinity. That y value is going towards positive infinity every time. Huh? There's 4 different ones. So, I could also, just like in the problem we just looked at, have a degree that's even, and a leading coefficient that is negative, and I'm going to get a graph that looks something like this. Again, I'm only talking about the end behavior. it may look entirely different in the middle. There may be a bunch of terms, there may be who knows what, but the ends will look like this. Your end behavior will be the limit as x approaches negative infinity of f of x equals negative infinity, and the limit as x approaches positive infinity of f of x equals negative infinity. Okay? So when you have even degrees, they go to the same direction. The end behavior goes the same direction, and it's whatever the leading coefficient is. If it's positive, they both go up. If it's negative, they both go down. Kind of makes sense. Okay? So now we have even degrees. What other type of degrees do we have? We have odd degree functions, meaning their highest coefficient is, or the highest degree is 1, 3, 5, 7 odd numbers. Alright, so you could have a degree where it's odd, and a leading coefficient that's positive. Okay. Those types of functions are always going to have this type of behavior. Okay? They're always going to start down low, end up high. So you're always going to have the limit as x approaches negative infinity of f of x is equal to negative infinity. The limit as x approaches positive infinity of f of x is equal to positive infinity. And finally, you're going to have functions where the degree is negative, or the degree is odd, and the leading coefficient is negative, and you're going to have graphs like this. And again, only the end behaviors are going to be always the same. The middle may look entirely different, right? And so what you're going to have is the limit as x approaches negative infinity of f of x is equal to positive infinity, and the limit as x approaches positive infinity of f of x is equal to negative infinity. And again, every time you have an odd degree function with a negative leading coefficient, that's the end behavior. Okay. Now, that's like a little shortcut / rule for polynomials. Okay. Now, on your homework, you're given the graph, so you can just look at the graph. But that right there is something that's important to know. All right. So here's the thing: these are polynomials. They go up to negative infinity and positive infinity, or whatever. You're going to have functions that don't do that. You're going to have functions that go to a specific value. The end behavior might be 2. The end behavior might be -1. Might be 0. Okay. So what I want to do is I want to look at an example of that. Okay. So you guys again, for your homework on polynomials, they're going to give you the graph. You just look at it. You tell them what their behavior is. For these next ones, you're going to have to look at it. All right. So you have the graph of x divided by x squared minus 2x plus 8. You're going to have to graph these. I'm not going to tell you the shortcut right now for this. You're going to learn the shortcut and figure out this end behavior. Not really a shortcut to more rule. Like find out in a couple weeks. All right. So on this problem, this is actually going to be approaching a actual value. Alright, so what we're gonna do, we're gonna graph this again. Okay, so we're gonna have y equals, we're gonna clear all that out. I need to do x divided by parentheses x squared minus 2x. Make sure I get x squared minus 2x plus 8. Okay. I'm gonna, before I graph it, I'm gonna hit zoom 6. And now I'm gonna hit zoom 4. Alright, let me figure out Alright. So, you can look at this. Yeah, I want you guys to, if you look at this graph, what does it appear that as x approaches negative infinity, what does it appear to be getting? What does y appear to be getting? Negative infinity? I'm going to cheat here, guys. I'm going to use their little window that they got up here, which is a pretty good one. Second window. And I'm going to go min x values is negative. And count and then 1 and then make that 1. And 1 and negative 1. And then 1. And then we're going to make this 1. How do they get that? I don't know. You know, they make it work. So, grab it. Okay, now what does this graph look like as we go to negative infinity? As x approaches negative infinity, what is it kind of right approach? So it comes here, it's going down, and then it starts going back up a little bit. Let's see this. I'm going to see this helps just a little bit. Let's do negative 15 and 15. Okay. So, what do you think? What do you think this is being posted? 0. So we're going to make. So we'll make our guesses. So it looks as though the limit as x approaches negative infinity of f of x, so the y value is getting close to 0. That's our estimate. What about on the right hand side as x approaches positive? What does it look like it's going? 0. Okay, good. Now, this one's a little bit trickier. Alright? So again, I'm not telling you guys a shortcut here. So like it's a little bit like I look at that and I see, yeah, it's definitely approaching 0, but as x goes for negative infinity or positive infinity. I know that because I know the rule for this. Alright? But what we want to do now, okay, is we need to confirm this algebraically. Alright? How do we do that? Well, the easiest way for you guys to do this is to choose a very small number that's negative and a very big number. So, we'll have Leilani, you choose a really small number. 5.
That's like really small.
Like really, that's really big. Small. I need a really big, you know how like if you don't have when you're in debt, you get really bad debt.
Oh, okay.
Negative 500. So Leilani's negative $500 in debt. Someone give me a really big number. 1,000. Okay, I like it. Mine's like 5. That's not that small. Alright, so to confirm this algebraically, we need to plug these in. Now, I don't feel like typing is actually in, so what we are able to do is use our calculator. So we're going to go second window. We want to see negative 500, so we're going to type in negative 500. And I'm going to hit second table, and it says negative 0.002. Now, I had to guess. That's getting pretty close to, if I continue going up, alright, obviously, now it's at negative 0.019, so, I mean, obviously, now it's at negative 0.0018, it's getting smaller, it's getting close to zero. So we said this is negative, the calculator rounded and said it's negative 0.002. That's pretty close to zero, right? Now, what do you find in your calculator? Second, table set, we're going to 1,000. We're going to hit second graph. Okay, so now it's at 0.001. So 0.001. Is that approaching zero? Yes. As I continue to go down this way, alright, now it's getting really small. Alright, so it's approaching zero. So our estimate was of zero was correct. Alright? So that's how you check. So you make your estimate. You write down what your estimate is. You check it algebraically by finding a very small number and a very large number. If your estimate is wrong, okay, now you actually know it. Now you know what it is, so you can just fix your estimate, right? So let's say I had typed both these in and it said like 2.0001. Well, okay, obviously it's probably getting really close to 2. So then I'll put 2 there for both of these. Alright? For instance, I can do this. If I change one couple things, I'm going to go to second, 2, and then watch. That's how it works. There's a lot. So, let me do this. So, first of all, I need to not count by 0.2. Let's just go down. So, negative 3, let's count by 1. So, that obviously, as x approaches negative infinity, what does it appear the y value is approaching? Does it appear that it's approaching positive infinity? So here, let's just look at this. Let's actually take this as an example. Oh, well, I did give you guys the shortcut. Then you guys got to get the shortcut. But so let's look at this. If we take this graph, so maybe we say, okay, yeah, maybe so this is 2x squared divided by x squared minus 2x plus 8. Okay, so if we look at this, I heard someone say, okay, as the limit as x approaches negative infinity of f of x, I heard you say positive infinity. I'll put a big question mark here because it's not positive infinity. Alright? The limit as x approaches positive infinity up for f of x. What do you guys think is approaching over here? Remember, these are 1, 2, 3. Look at that. It is going back down. So what's it going back down towards? So maybe 2. So what do you think this really is? I'm thinking it's probably 2. So if we look at this, how do we check? So we have checked by, we need to find the limit as or we need to find the function value at, let's say, negative 500 and 1,000. We already started on 1. All right. So pull back up our calculator, and we want to figure out the y value for negative 500. So we go to second table set. We go to negative 500. Hit enter, and go to our table. 1.992. If I need more proof, maybe I'm not convinced, I can go second window, let's try negative 2,000. Second table. Oh, negative, or you said I need to go to 1.998. It looks like it's approaching 2. If I get it going, I might get to 1.999 real quick. Sometimes, maybe not real quick, who knows. But clearly, it's going towards 2. Right? I know, now we check over here, we check 1,000. We have a second window, 1,000. And we hit second table, 2.004. And if I keep going up, it would slowly get closer to 2.000. Alright? So, I give you shortcut now, Taylor. Hold on a minute, hold on. Here's the shortcut. This was better going on. You guys got to switch and magic on that. So, here's this one. Did you guys see that? This is the cheat sheet. Alright, and behavior cheat sheet for graphs that approach a specific value. Alright? So, if the degree of the numerator is greater than the degree of the denominator, the end behaviors approach positive or negative infinity. Okay? If the degree of the numerator is less than the degree of the numerator, or the denominator, the end behaviors approach y equals 0. If the degree of the numerator is equal to the degree of the denominator, end behaviors approach y equals a divided by b, where a and b are the leading coefficients. Then behaviors approach positive or negative, or positive or negative. Alright, so if we go back up and look at this one, okay, we saw both graphically and algebraically that the end behavior as x approaches negative infinity and positive infinity was 0. Okay? Now if you look at this, when we come back down here, you see that in all of these we're comparing the degree of the numerator to the degree of the denominator. So if we go back up here, what is the degree? So here's our numerator up here, in red, right? And our denominator down here in green. Right? So what is the degree of our numerator? What is the highest degree in our numerator? Which is raised to the degree of what? 1. Right? So the degree of our numerator is 1. Now, what about the degree of our denominator? What is the highest degree? 2. So, we compare these two. Alright? You know why the degree of degree of this is 2? Without it. This exponent right here is 1, so how is not 1? Okay, so if we look at this and compare these two degrees, the degree of the numerator is less than the degree of the denominator. So I come down to here. If the degree of the numerator is less than the degree of the denominator, then behavior approaches y equals 0. Okay? Now, let's look at this problem right here. Alright? 2x squared divided by x squared minus 2x plus 8. My numerator is right here in green. The degree of that is what? 2. And my denominator, right there, what's the degree of that? 2. Okay. So, my degrees are equal. So I have, if the degree of the numerator is equal to the degree of the denominator, then the end behaviors approach y equals a divided by b, where a and b is the leading coefficients. So a is the leading coefficient of the numerator, b is the leading coefficient of the denominator. So you come up here. What is the leading coefficient of the numerator right here? 2. So I have a divided by, what is the leading coefficient of the denominator? 1. 2 divided by 1 is equal to 2. What did we say in the behavior was? 2. Right? That makes sense. So, if I had this function right here, I want you to, on your paper, do this by yourself real quick, take 15 seconds. Okay. Again, you're looking at the degree of the numerator and the denominator. And so we'll make the answer. Simply have an answer. Okay. So, Lucas, how'd you get that?
I realized that the two degrees were the same, so it's along the legal grid and coefficient, which is nothing but a bottom, so I'm going to negative 3.
Negative 3 and
Negative 6, actually.
So, you do that, and what you say is, you know, the limit as x approaches negative infinity, f of x is equal to negative 3, and the limit as x approaches positive infinity, f of x equals negative 3. Okay, now, in your homework, okay, in your homework, it gives you these types of functions. We have the numerator and the denominator. That says find that behavior. I'm perfectly fine if you say, the end behavior is this and this because, and then say, the degree of the numerator is equal to the degree of the denominator. You don't have to like actually show me the math. So as you can come up with this conclusion, and then explain using this and find it. So that's the first part of your homework. Now, next part is pretty easy. Okay? So we're going to switch sort of topics. We're just talking about end behaviors, limits, and continuity. What I want to talk about now is increasing and decreasing behavior. It's easy. You guys know how to tell if something's going uphill? Good. Downhill? Good. Not doing anything, just being constant? Good. Okay? So, a function, and this is, again, all we're doing is we're going to analyze these functions. Okay? First of all, you read a function from left to right. Okay? So what we want to look at is we're going to consider that graph of that effect that's shown right there. Okay? And as we move from left to right, what we would say is f of x is increasing or rising, right? We're going to stick with the word increasing though. Increasing on the interval negative infinity to negative 5. Which means that when see this arrow right here is saying it's going down, it's like down here, all the way down to negative infinity. So it is going, if you're walking on this graph from left to right, you'd be walking, like, I'm not in my hand walk, but you'd be walking uphill. Right? So it's harder than you'd be going uphill like this. Okay? This graph right here is constant or flat from negative 5 to 0. Why is it constant? Because it is a flat line. It's like I'm not going up or down. Okay? The y value is staying the same. And it is decreasing or falling on 0 to positive infinity. Okay? Right. So again, so for you guys, you're going to be looking at graphs and figuring out if it's increasing or decreasing. In calculus, or in your first college math class, you will actually have a strategy, have a topic, an idea that allows you to actually figure out if the function is increasing or decreasing without even looking at the graph. All right? Very clear. So, questions on like what increasing and decreasing and being constant looks like? No? Okay. Now, you have that down for the most part, and there you guys move. Then you go together, okay? You got it? You can do everything all that. So, we're going to do a couple of examples. This is a quick one. Okay, so we're going to look at these examples real quick. Alright, so the first example we're looking at is 2x to the third power, negative 2x to the third power. So, again, you guys don't know how to figure out if it's increasing or decreasing or constant unless you're looking at your graph right now, because why you're not in calculus. Alright, so the graph is y equals negative 2x to the third raised. I just throw that out. Negative 2x raised to the third power. I'm going to grab it. I hit the 6 real quick. There's my graph. Okay? Maybe, I'm going to zoom in just real quick, just because it's not funny. There you go. Okay. You hold that? Okay, I like that. Decreasing, constant, decreasing. This function looks like it is constant right in the middle, does it? Right? Doesn't it? No. Okay. It is this function. So first I'm gonna say it's not constant, and then we'll zoom in and we'll look at why it's not. Alright? But reading it from left to right, if I'm driving the car down, or if I'm driving the car on this graph, am I going uphill or downhill the entire time? Downhill. So it's asking, so is this function ever increasing? No. So I don't need to write anything that it's not increasing. Right? It is decreasing over the interval, so from negative infinity to positive. I'm going to ask you guys this real quick. Okay? That negative infinity to positive infinity, are those x values or y values we're talking about? It is the same. So what this is saying is that, so when we're describing this, right, we're describing this, we're saying, these are the x values. Negative, x equals negative infinity all the way to x equals positive infinity. Those are the values where it's decreasing. We're not describing the y values, because if we were, we would have said something else here, but we're saying, on this first example, we're like, it's increasing from negative infinity to negative 5, which is our x value. Here we said it's constant from negative 5 to 0, so our x value is decreasing from 0 to infinity, 0 to infinity. We're always looking at x values. We're describing this, we're describing the behavior, increasing and stuff like that. We're always talking about what is the x value where it's increasing, what is the x value where it's decreasing. Alright, so x cubed minus 3x. Got that? X, that's not x. X to the third power minus 3x. And I do 6. Yup. Okay. So you guys have, so you have this graph right here. Okay? Now we're looking at this. Here's the thing. Right now, you're just going to sort of estimate these things. On Wednesday, we're going to talk about how to actually find this exact point. Right? But if we're looking at this, we had to make some estimates here. On your homework, it's going to say make estimates to the 0.5. So if it looks like it's in between 1 and 2, you're just saying 1.5. Alright? So if we're looking at this, you actually make it bigger. Okay, so, was that? No, that's not what works. It's just playing games on it. So, it wouldn't matter even if it wasn't. So, well, yeah, I guess it would matter. It's kind of what it wants. So, this function, first of all, is it increasing anywhere? Just yes or no. Is it decreasing anywhere? Is it constant anywhere? Okay. So it is, so we know it's increasing. If you guys did what x value over what x value would you say is increasing? So negative infinity to what? To negative 1, because right there is negative, that's x equals negative 1, so you go up and this, that's like negative going down. And then where else is it increasing? You guys look at the y values, aren't you? Negative 2 to infinity. 1 to infinity. That is the biggest mistake that I guarantee on the first quiz that if there's a mistake on this, that's going to be a mistake. X-axis. You're always looking at the x values when you're describing increasing, decreasing, and constant. I guarantee you, someone will make that mistake on the quiz. Don't be that person, because now that everyone's going to know that, I'm going to go onto the YouTube video and comment on which person made the mistake, and then call you out on YouTube, and everyone's going to know that you messed up, even though I told you not to. No, I'm going to make like this bump right here. It owes me $8 million. Who's got this wrong? Alright, now decreasing. Where is it decreasing? Negative 1 to 1. Alright? Negative 1 to positive 1. Okay? Any up? Huh? No, that's count by one. Trust me. Look, see, I can do this. Window, count by ones. Oh, wait. Huh. Oh, yeah, you grab there. Maybe not. That's just shadow. All right. Questions about that? Let me get it. Oh, no. So this is one of the problems, just like what your homework's going to be. All right. Notice, so, I don't know. Okay, whatever. Here's just another example. Right? First of all, if we look at this function right here, is it increasing in here? Yes or no? Okay, is it decreasing in here? Is it constant? Okay, good. So constant on 7. So increasing on what x values? X values is it increasing? What interval? Yes. What? Yeah. So 2. So x value is 2. I think people think like this right here. I got that one. Okay. So 2 to infinity. Okay. What about decreasing? Huh? You're saying infinity because the y value is negative infinity. Okay? Question. Now, your homework says they support your answer numerically. Yeah. I don't need to do that because what they really want you to do is like create a table where it's like you choose like 4 x values and just like say, okay, look, see the y values going down. I got a graph. Clearly it's going downhill from here from this negative infinity to 2. Okay, clearly I don't need to go on it make a table. That's doing too much. Alright? So this is just a little tidbit. So typically for you guys, you're only going to be able to really figure out when a function is increasing, decreasing, or constant, whether or not, or when you have a graph. Okay. If you don't have a graph, you guys are probably SOL. Okay, that means stuff out of luck. And you need calculus to pretty much start talking about that without having a graph. Alright? And you guys won't learn about that right now. Maybe at the end of the school year we have time to talk about a little bit of that, maybe. But right now you guys will not have the tools that you need in your tool belt in order to figure out when a function is increasing, decreasing, or constant without having calculus, without the graph. Alright? So, homework. Your homework is, see on this paper where it says, you guys have the rest of page 30, so, and then page 41 through 10 even. That's your guys' homework. Alright?